Good morning. I'm Junichi Yamabe from Kyushu University in Japan. So today, I'd like to introduce our recent result regarding particular growth property of low carbon steel and the hydrogen gas as hydrogen with various environmental combinations of hydrogen gas pressure and test frequency and test temperature. So here is an introduction of my presentation showing recent topics of hydrogen energy society in Japan. In Japan, fuel cell vehicles have been commercialized and related to hydrogen stations are gradually constructed. So the hydrogen energy society is just starting in Japan. However, mechanical properties of metals are sometimes generated by hydrogen, well known as hydrogen embrittlement. Here is an example of hydrogen degeneration of low carbon steel and the hydrogen gas as hydrogen, showing the acceleration of FCG rate in presence of hydrogen. So in this case, 30 times FCG acceleration was observed in presence of hydrogen. So this data are obtained from at room temperature. Have many components operated not only at room temperature, but also some temperature. For example, elevated or lower temperature. So for the safety of the hydrogen components, hydrogen effects of materials and the various environmental conditions should be accurately captured. In this viewpoint, the objective of this study is to clarify the effect of hydrogen gas pressure, test frequency, and test temperature properties of a low carbon steel. So, experimental questions. We used a low carbon steel with a tensile strength approximately 500 megapascal with a ferrite structure. So from this steel, we manufactured conventional CT specimen, compactation specimen following the STM standard. So we performed FCG test and various combinations of test temperature, test frequency, hydrogen gas pressure, and test temperature. So the test frequencies range from 0.001 Hz to 1 Hz. And the hydrogen gas pressure range from 0.1 to 90 pascal. And the test temperature range from room temperature to 150 degrees C. And two types of HCG tests were performed. One is delta P constant test, P means load. And the other test is a delta K constant test. From the delta P constant test, we obtain a conventional HCG properties. And from the delta K constant test, we investigated the effect of hydrogen test temperature, also test frequency of the HCG rate. After these tests, simple deformations were observed by using optical microscopy, and fracture chart morphology was identified by using the scanning electron microscope. So here is a high pressure hydrogen fatigue tester using in this study. So this is a photograph of the tester. The maximum hydrogen gas pressure is 140 megapascal, and the maximum temperature is 600 degrees. So in order to mitigate the oxygen effect of HCG property, we use 99.999% high purity hydrogen gas. As a result, the measured oxygen content in hydrogen gas is always less than 1 ppm. So this content satisfies some standards. So we can say this test can be ignored. This test ignores oxygen effect on the HCG rate. So let's go to the result of this session. This figure shows the HCG properties of low carbon steel in hydrogen gas as hydrogen at room temperature. So at the delta K values ranging from 12 to 20 around here, increasing the delta K, the HCG rate in present hydrogen was more accelerated. And at the delta K values ranging from 20 to 40, the delta HCG curve in present hydrogen was parallel to those of air. Next, we need to clarify the effect of hydrogen gas pressure on the HCG rate. So this figure shows the relationship between relative HCG rate and the hydrogen gas pressure. So the relative HCG rate is defined as the HCG rate in presence of hydrogen to the HCG rate in absence of hydrogen. So except for hydrogen gas of 1 megapascal, the relative exchange rate was not dependent on the hydrogen gas pressure. Next, this slide shows the effect of test frequency on the FCG, relative exchange rate. In this case, a peculiar dependence of the exchange rate on the test frequency was observed. At a relatively high test frequency, around here, the relative exchange rate was increased. However, at a relatively lower test frequency, a very peculiar dependence was observed around here, depending on the hydrogen gas pressure. So, at the hydrogen gas pressure of 90 megapascal, shown by square, with the decrease in the test frequency, the relative exchange rate was increased. However, at the hydrogen gas pressure of 45 megapascal, shown by square, 90 megapascal circle, and the 45 megapascal is square. Irrespective of the test frequency, relative exchange rate showed constant value. In contrast, hydrogen gas pressure of 10 megapascal or lower, with the decrease in the test frequency, the relative exchange rate was decreased, showing the exchange rate in presence of hydrogen was nearly equal to the exchange rate in absence of hydrogen. Very interesting result. So in order to interpret this peculiar dependence, we observe slip deformations, especially by using optical microscope. So these three images are magnified once at these three regions: air and gaseous hydrogen. In air, slip deformations are formed at a wide region around the gravity. In this case, in presence of hydrogen at the test frequency of 1 Hz, slip deformations were localized around the gravity. In this case, exchange acceleration is produced. In this case, in presence of hydrogen, however, slip deformations were not localized, as well as those in air. So in this case, no exchange acceleration is occurred. So this result implies that exchange acceleration by hydrogen is attributed to localized slip deformations by hydrogen. And next, I would like to introduce a fracture surface morphology. So this morphology is obtained from the special testing in air. So ductile, ordinary striations were observed. Here is a schematic illustration, conventional schematic illustration of striation forming. So next, these are fracture surface morphologies testing in hydrogen gas. These two images correspond with these relative exchange rates. So exchange acceleration occurs, and the exchange acceleration is not produced. So in this case, different from striations in air, obscure striations were observed. However, in this case, ordinary clear striations were observed. Next, I would like to introduce a result of the specimen at elevated temperature, 90 degrees C and 150 degrees. So this is a very interesting result. Actually, from this figure, with the increase in the test frequency, the onset of the onset of the hydrogen-assisted exchange acceleration was shifted to a higher delta Q value. Okay. So these are slip deformations observed in the specimen. Room temperature 90 degrees C and 150 degrees. This is a specimen obtained from nitrogen gas. These are relative exchange rate, 14, 9, and 3. Corresponding with these relative exchange rate, slip deformations are changed. So localized slip deformations are related to hydrogen-assisted exchange acceleration in elevated temperature. Based on these experimental results, I want to describe this acceleration by using this model, HSHG model, hydrogen enhanced success FCG model. So this is the crack growth behavior in air, whereas this is the crack growth behavior in presence of hydrogen. So there are two important points of HSMCG model. One, slip deformations are localized at the crack tip by hydrogen, and the crack maintains a sharp shape without crack broadening with the localization of slip deformation by hydrogen. Due to this model, we consider slip deformations are produced and FCG acceleration occurs in presence of hydrogen. Furthermore, based on this model, I want to predict the onset of FCG acceleration by hydrogen. As mentioned, FCG acceleration is caused by slip deformation by hydrogen. So these slip deformations are presumed to be caused by a localized hydrogen concentration. Therefore, I want to introduce a parameter representing a gradient of hydrogen concentration at the crack tip like this. So this value can be calculated by using saturated hydrogen content and hydrogen diffusivity. So these values are obtained by using a crystalline specimen with severely deformed condition. Like this. And anyway, when this value exceeds a critical value, we consider the hydrogen acidity FCG acceleration occurs. So based on this model, I predicted the onset of FCG acceleration in presence of hydrogen. So these four plotted data correspond to the onset of FCG acceleration by hydrogen. Therefore, if these four plotted data can be fitted by this curve, we can say our model is appropriate. So as you know from this figure, these plotted data are roughly consistent of this curve. Therefore, the onset of hydrogen acidity FCG acceleration and the various environmental condition can be predicted by using a novel parameter representing the gradient of hydrogen concentration in the crack. So here's the conclusion of my presentation. There are two important conclusions. The one conclusion is that hydrogen acidity FCG acceleration always accompanied the localization of plastic deformation in a crack tip, and it was inferred that a steep gradient of hydrogen concentration causes a slip localization at crack tip. The conclusion is that the peculiar dependence of the FCG rate on the hydrogen pressure, test frequency, and test temperature could be unified by using a novel parameter representing the gradient of hydrogen concentration in a crack tip. So thank you for your kind attention.